Hi, everybody. It is my great honor. I apologize, I'm come here late, but it's my great honor to introduce Dr. Paul Ohodnicki. Paul has been working with me for many years. Hopefully I pronounced his name right. I know Paul when I just come to Pitt. He was the first student to sit in my ECE 1232 photonic class. I remember him really well because he did A+ in my class. I always actually brought this up. The other student I remember well didn't do quite well in my class, but he became a lawyer. So I end up to work with him on my invention and the patent case. So now I learned from this lesson saying that I should never treat a student badly. So Dr. Ohodnicki is, I consider him the best researcher within the National Energy Technology Lab. He actually had done many things in his career, but he really is the research champion within the organization of NATO and push research in many fronts, including the quantum science, which is subject of this seminar, and the fiber optic sensors, also artificial intelligence, and he started many very active, successful program within the NATO. And we are very lucky to, Swanson School of Engineering is very lucky to recruit him to start a career here at Pitt. And just as he started, his first proposal was supported, right? That's from APE. That's a $1 million grant. So you can see that he is exceptionally good in getting grant, but also he has many good ideas. Today, we're going to have opportunity to hear some of his idea in quantum science. And Paul, the floor is yours. And thank you to provide time to talk about your research.
Yeah, thanks, Kevin. So I really appreciate the introduction. I have worked with Kevin for a long time. So about half of this talk is on fiber optic sensing, and my first photonics class was with Kevin. So I also benefited from Kevin very early on as well. So I'm just going to go ahead and jump into this. So the title of this talk is Emerging Energy Infrastructure Sensing Technologies and Opportunities for Quantum. The idea is to give kind of a broad overview of different thrusts in sensing for energy infrastructure monitoring. And then at the end, I'm going to give some perspectives on some of the things that we're thinking about in terms of opportunities and also challenges for bringing in quantum sensing techniques into these types of platforms. I did not prepare this material just on my own. A lot of collaborations with colleagues from the NETL
Paul,
to pull that together.
If you want to, if you have slides that you want to share, you can.
Oh, it's not sharing yet. Yes, let me share. 1 second. I thought that the finger puppet show would work, but we'll go with slides instead. All right. So we'll go ahead and get started here. So this is an overview of some of the colleagues who helped to contribute. What I'm going to talk about is the basic idea of sensor needs for energy infrastructure monitoring. Then we're going to jump into some developments and trends with classical sensor technologies, and I'm going to focus on 2 platforms. The first one is passive wireless sensors. The second one is optical fiber sensors. I'm going to try and motivate why these platform technologies are very relevant for energy infrastructure, and then some initial thoughts on opportunities and challenges for quantum, which were really developed by the group here. So before I do that, I wanted to make people aware we actually have published a large number of reviews in recent years in the area of energy infrastructure and sensing, and so I encourage you to take a look. So these are 3 examples. The left-hand side is distributed optical fiber-based sensing. It's a review on the topic of distributed optical fiber sensing. The center one is SAW, surface acoustic wave sensors for chemical vapors and gases, which has been a recent trend. It's a very highly cited publication, actually. It's on track to be one of my most highly cited, and that was written by Jagan in collaboration with myself. And then state-of-the-art methane sensing material. So as it turns out, methane is a very important molecule, but it's also a very challenging one to be able to measure. And so this review article talks a little bit about some of the opportunities and challenges for methane sensing. We also have a review that was published on corrosion sensing, which is the one on the left-hand side. So this looks at corrosion across the oil and natural gas infrastructure. We looked at transformer monitoring, so chemical sensing to look at electrical asset monitoring in the center. and then a review and perspective on extreme high temperature fiber optic sensing on the right. So these are all really good review articles. I definitely encourage you, if you wanted to understand broadly the area of sensing for energy, these are all really good references for you, both breadth-wise as well as depth. So let's go ahead and jump into what some of the applications are. The type of researcher I am, I always focus on the applications and impact and then try and find really good science that connects with that. So if we talk about in the energy space, one of the primary challenges that we look at is how do we make conventional power generation more efficient, more reliable, and now as we get more renewables on the grid, we're also trying to make it more flexible as well. So this could be power plants, which may be fossil or nuclear. This could be electrochemical based, like fuel cells, combustion systems, gasification, gas turbines. What really ties all these applications together is very high temperatures, very aggressive environments, parameters like temperature, gas phase chemistry, pressure, and acoustics are all parameters that are really ubiquitous across these spaces. So another example set of applications is in the area of renewable energy generation. This one isn't quite as obvious, but even for applications like photovoltaics and wind, the amount of energy they can produce is directly related to the weather. And so the ability to measure parameters related to weather, whether it's irradiance or whether it's wind speed, and to be able to incorporate that into predictive models allows for better managing the variability that we would otherwise see associated with those sources. Solar thermal is an example of a very high temperature solar generation technology that starts to look a lot like a conventional plant because it's a thermal based generation process. So again, high temperatures. In this case, you have thermal working fluids like molten salts that are very aggressive. And then for geothermal, this is a subsurface based generation approach. High temperatures, kilometers into the depths of the earth, and so being able to measure things very deep in the earth, below the earth's surface, and bring that information to the surface. Having instrumentation which is robust to measure temperature, pressure, acoustics, seismic activity are all relevant. Another area in energy is energy and resource recovery. So this includes oil and gas, both onshore as well as offshore. So for onshore applications, we're typically talking about kilometers below the earth, ones to several of kilometers below the earth, high temperatures, 100 to several hundred degrees Celsius, high pressures on the order of several thousand to 10,000 psi. Again, being able to measure chemistry, the pH in the subsurface environment, being able to measure temperature, acoustic activity, so particularly in the case of fracking, we want to understand how the fracture network forms, and so understanding local emissions, acoustic emissions, allows us to better understand that. In the case of wellbores, doing wellbore integrity monitoring, whether it's the metallic casing to prevent it from corrosion, or the cement which surrounds the casing to try and prevent degradation of the cement as well, and then also environmental impacts monitoring. And then the final broad area of energy infrastructure is what I would call energy transport and storage. And so this is an area where we're looking more at taking energy that we've already generated and we're storing it, or we're transporting it from point A to point B. This could be on the electrical system side, like the transmission and distribution system. This could be on the pipeline side, like hydrogen, natural gas. As it turns out, hydrogen is something that's an increasing topic of interest across the DOE offices right now. The bottom left is an example of transformers, which are basically stations which convert voltages from lower voltages to higher voltages on the transmission and distribution system. So they're critical junctures within the electrical transmission system. And then storage. So grid scale energy storage is something that didn't exist decades ago. Now it's something that's becoming critical to allow us to best manage flows of electrical power as well as variabilities associated with renewable sources. So all that said, that's some examples of some of the types of applications that are relevant for energy infrastructure monitoring. If we want to measure some of these parameters that are of interest, we first have to define what we mean by a sensor. So when I think about a sensor, this table kind of classifies it. So we have a number of attributes that we care about. These attributes include the cost of the sensor, what information it gives us, geospatial, which means that how do we measure things and where do we measure things, how do we get that information and send it to where we need it, how do we power the sensor, and then how do we worry about any potential cybersecurity risks. So different types of sensors have different classifications of these metrics. And when I look at a sensor network, this is the type of approach that I use. And so what you want to do is first, you want to think about, for a particular application, what are the parameters that are most relevant for that application? So here's an example of natural gas pipelines or transmission lines. So these are infrastructures which are very long, 50, 100 kilometers in length. We're interested in measuring information all along the length of a pipeline. And we also don't want to have to worry about cybersecurity risks. So if we look at this, we would typically measure the information's cost basically per unit node, because the infrastructure is so large that we're not worried as much about the total cost, but we're worried about how much cost per meter or per kilometer of our pipeline, for example. We'd really like to get as much information as we can, and because it's such an expansive piece of infrastructure, we may get into big data issues. The geospatial attributes, a pipeline is a line, a transmission line is a line, and so we really want sensing with line capabilities or linear characteristics, but multi-point characteristics may also be suitable as well. In terms of telemetry, we don't want to be running a wire along a pipeline. We don't want to have to run wires along transmission lines if we don't have to. So either optical-based wired, meaning optical fiber, or wireless-based approaches are preferred. And then in almost all cases, from a power perspective, we'd prefer for it to be passive. In terms of cybersecurity, because with a pipeline or a transmission line, we're typically taking information that's measured all along the length of the system, and we're accumulating it. We may either have direct use of that data in some type of central station, or we may have direct transmission along the length of that. And so for those two, that impacts the total cybersecurity risks that we would have to be concerned with. Notice that for subsurface oil and gas, it doesn't look that different, right? The only difference is, I would say, that for subsurface oil and gas, because we only have 1 to several kilometers, the total cost is important, but otherwise it has a lot of similar characteristics as pipelines. If we look at transformers, for example, or energy storage, though, it looks very different. Now we have to worry about communicating with these because these are discrete devices on the system. We may be just worried about one parameter, temperature. We may be worried about multiple parameters. We're typically interested in point measurements, maybe multi-point, but these are individual discrete devices, so we're not as concerned about linear measurements. Wireless telemetry tends to be most compatible because we're not just sending information from point A to point B. We have to send information or accumulate it from a number of distributed devices out in the system. Again, passive, and we have to worry about distributed data transmission. So this is one reason why, in the case of things like transformer monitoring, electrical asset monitoring, the whole issue of cybersecurity becomes extremely important, because we have to find a way to either use the data locally or accumulate it. Okay, so with all that said, let's talk about one of the example of sensing platforms that's very prominent for energy infrastructure monitoring. So this is the area of wireless sensing. And in wireless sensing, we're basically looking at having a number of distributed sensors uniformly distributed throughout a system. They collect information about the local environment, and then they'll wirelessly send that information back to some kind of interrogation unit for processing. Passive sensors are ideal because they don't require active power. We can interrogate them when we need to. But one of the big challenges with wireless sensors is the ability to communicate with them. One of the big trends in this space right now is the area of 5G. 5G doesn't stand for 5 gigahertz, but it just so happens that that's right in the middle of the 5G frequency spectrum. But in general, 5G does refer to higher frequencies than previous versions of wireless networking. So this introduces new telemetry challenges, but as I'll talk about, it also introduces some opportunities as well. In terms of different types of sensors, we can have passive wireless sensors that are oscillating circuit-based. So these are basically active devices that harness energy, and then when they have enough energy, they'll use that to perform their sensing function. RFIDs, I think most are familiar with. Surface acoustic wave sensors are the types of sensors that I've spent most of my time in the passive wireless sensor area. When you want to communicate with sensors, you need to interrogate them. One of the big challenges is the range over which you can communicate with passive wireless sensors. So let's go back to this idea of attributes. So if we look at the attributes of a passive wireless sensor, we typically are thinking about the information of the sensor itself per node. We would measure at least one parameter. In many cases, these devices can be modified to measure multiple parameters. It's inherently a point measurement. It's also a wireless measurement. It's passive, and it has a distributed data transmission characteristic. So if we look back at some of those applications that we looked at before, we see that this seems to match up reasonably well with things like distributed measurement of energy storage on the grid, distributed measurement of transformers. And so what you see is that these are some of the application where some of these types of passive wireless sensors are becoming more prominent. Okay, so into some of the technical aspects here. So the passive wireless sensor platform I've spent the most time with is called the Surface Acoustic Wave Platform. These are a very mature set of devices. The reason I like working with them is that you can integrate, so you have a piezoelectric substrate. This substrate, you excite it with interdigitated electrodes in the RF range. That creates a propagating acoustic wave because it's piezoelectric. If you integrate a sensing layer onto the device, then the integration of that sensing layer now causes a response. So that response could be based on the mass, it could be based on the elasticity of the sensing layer, or it can be based on the conductivity. And so if you identify materials that interact with the environment and have an associated mass, elasticity, or conductivity response, these devices can be modified for a wide range of applications. So some of the example applications over the years, CO2 monitoring and methane monitoring, obviously very important for energy applications. This is an example of a metal organic framework layer integrated onto a surface acoustic wave device. These are very highly porous. They're nanoporous structures. The pore structure can be tailored because of the flexibility of these hybrid inorganic organic materials. They have a physisorption-based response, so it's a very reversible response. It's a very rapid response, and it's really ideal from the perspective of chemical sensing. So we've been able to demonstrate over the years that these types of devices have a very nice response to CO2, and we're also looking at modifying them to be responsive to methane sensing as well. This is an example publication which just came out this year, which was looking at devices which were optimized in the 860 megahertz range. So this is an example of a set of devices which were fabricated with an antenna. This is just a small demonstration of Jagan, who's the one who has spent the most time developing these over at the National Energy Technology Lab. This shows the phase and the amplitude that's being measured for the remote interrogator of the device. This is him installing the device onto the antenna. It's sensitive to CO2. He just happens to have a point source of CO2 readily available. And you can see that the phase as well as the amplitude of the device shifts in response. So in addition to measuring single environmental parameters, you can also measure a wide array of materials as well. And you can integrate those materials onto a single device. So this is a version of an electronic nose, except it's passive, it's wireless, and it's miniaturized. And this is kind of an emerging area in the field of surface acoustic wave devices. I actually worked on this a good bit with Chris Wilmer before I joined Pitt, and I'm continuing to collaborate with him in this area now. He's actually using some physics-based and chemistry-based algorithms to identify what the optimal combinations of metal organic frameworks would be. But in any case, this is some preliminary work that shows devices which are fabricated which allow for integration of multiple sensing layers. There's also the opportunity to use these devices for liquid phase monitoring. The challenge with liquid phase monitoring, though, is that because this is an acoustic device, unless you modify the standard operation of the device, you'll lose a lot of energy to the solution phase because of the interaction of the acoustic wave on the surface with the surrounding medium. The solution to that is to use an alternative orientation of your substrate, which creates what's called a shear horizontal acoustic wave. So the acoustic displacement is in the plane of the surface acoustic wave device. That allows you to operate in solution phases, and that allows you to potentially extend these types of devices to applications like pH sensing in well bores or pH sensing in carbon storage applications, for example. These devices can also be used at very high temperatures. So this is a field where it's again newer and emerging for this class of devices. There are some established faculty, particularly up at University of Maine, that have demonstrated temperature sensing up to 1,000 degrees Celsius, for example. In the area of chemical sensing, the current limit is about 500 degrees Celsius. And this is an example publication from back in 2013 where we were looking at integrating metal oxides onto the device to be sensitive to oxygen for combustion applications. Now, the challenge is, so these devices can be optimized, they can be designed, but unless you can communicate with them and unless you can interrogate them, you're not going to be able to really deploy them within the energy infrastructure. So there's also been a lot of work looking at how can we optimize that communications interface. especially if we're talking about things like a pipeline or a wellbore. You know, again, it has a linear characteristic. How do we communicate with a number of devices that are actually deployed within the system? So there's some unique ideas. One involves, for example, launching waves internal to a pipeline and then allowing the pipeline to act as a waveguide. The second is having distributed antennas where you can actually have a coax cable, for example, where you tap into the guided electromagnetic field and you couple locally with a small fraction of that into local devices which are in close proximity. This is one example, as I said, where you have a pipeline. You may have, it could be surface acoustic wave or other types of passive wireless devices. You can excite a propagating electromagnetic field. It takes on a guided mode within the structure because it's basically a metallic tubular structure. As it turns out, if you were to try and do interrogation in free space, you may range over tens of meters for typical frequencies relevant for passive wireless sensors. In the case of a pipeline, if you're looking at 10-inch, 12-inch pipelines, they're sufficiently large to allow for propagation of typical frequencies that we would be interested in for passive wireless sensing, and in that case, you may be able to propagate for kilometers, for example. So it starts to make a lot more sense to use these types of devices when we have access to these advanced telemetry methods. So another thing that's interesting about the emergence of the whole 5G networking, wireless networking paradigm that we have right now is the high frequencies that are used for this type of a networking paradigm typically would be a problem from the perspective of telemetry because the shorter the wavelength, the faster something attenuates over a fairly short distance. So if we're trying to do long distance telemetry, it's a problem. But in the unique case where we're trying to measure something internal to a metallic structure, so let's say it's a pipeline or a casing or a boiler, it turns out that higher frequencies are beneficial because then we can actually propagate waves within that metallic enclosure. And so now you can start to envision wireless networks within a metallic enclosed structure like a transformer. So there's sort of some new ideas that can be explored moving into the future in that space. Okay, so that's a quick overview of some of the latest and greatest in wireless sensing for energy infrastructure. We'll now talk about the second platform that I've spent a lot of time on, and this is the one that I've actually worked on closely with Kevin Chen over the years, and this is the area of optical fiber-based sensing. So optical fibers have a lot of advantages. One of the unique aspects of an optical fiber is that it's not only the sensor, it's also the signal transmission medium. It's also compatible with what's called distributed sensing methods, and we'll talk more about those. They overcome the need for local power, and they're also suitable for harsh environment applications. One thing that's probably not talked about enough with optical fiber sensors is their cost, particularly when we talk about distributed optical fiber sensors. And so that's one of the areas where I think the field really needs to take a close look at how can we get the same information or enough information by reducing the cost of some of the instrumentation that we're using. But regardless, here are some examples of various types of optical fiber sensors that you can envision. So in contrast with passive wireless based, you have a lot of flexibility about what the characteristics of an optical fiber sensor are. So we can do point sensors. These are devices called fiber Bragg gratings or Fabry-Perot interferometers. We can do point sensors which are based on sensing materials that interact with light propagating down the fiber. We can also do quasi-distributed sensing where we take a bunch of point sensors and we place them along the fiber and we modify each of them so that we can identify the location as well as the signal. And then we have true distributed optical fiber scattering or optical backscattering based sensors. This is where we send a laser down a fiber and then we measure what gets backscattered back. This is very often Rayleigh backscattering, but it can also be Brouillon backscattering, and it can also be Raman backscattering as well. And each of these types of scattering physics has different advantages and disadvantages in terms of distributed sensing modalities. By measuring the backscattered light, we can then process that either as a function of time, or we can process that in the frequency domain, and that allows us to basically reconstruct parameters that we want to measure all along the length of an optical fiber. So this is how I would classify the attributes of optical fiber-based sensors. So they can be measured per unit information or node in terms of cost. We can look at total installed costs. Depending on what type of an optical fiber sensor, you may have tons of data like in distributed acoustic sensing. You may have a single parameter like a low-cost temperature sensor or anything in between. Again, geospatial, one of the advantages is that we can choose. Do we want to measure at a point? Do we want to measure at multiple points? Do we want to measure a line of information? These are wired, but they're wired optically. So a lot of the challenges associated with electrical wires are mitigated. And in fact, there's even some advantages, because if we talk about cybersecurity, one of the advantages of optical fiber-based is that it can't be accessed from an external agent trying to access that information. Whereas for wireless and arguably even wired, that can't happen. And so it's inherently a much more cyber-secure type of a sensing platform. And again, at least at the sensing location, the power requirements are passive. This is the example attributes for pipelines and for transmission lines. So we can immediately see why not in the area of research, as well as in the area of even industry, is starting to adopt distributed optical fiber-based sensing for monitoring structural health of transmission lines, monitoring structural health of natural gas pipelines. They're even using it for subsurface applications as well. Okay, so for some examples of sensors, one of the most straightforward types of sensors is a point sensor. This is an example of one that was published by a group at Virginia Tech. They just take a sapphire fiber, they put a wafer on the end. This forms a Fabry-Perot interferometer that changes the optical path length with temperature by measuring the corresponding spectrum, which is generated as a result of light being generated in a very high temperature environment and being measured through the fiber. They can calculate temperature. And this is an example of applying that sensor in a gasifier at temperatures which can be as high as 1600 degrees Celsius, where it was shown that because of the robustness of sapphire fibers and because of the robustness of optical-based sensors, they far surpass the lifetime of a traditional thermocouple in that case. So we can go from a point sensor to a quasi-distributed sensor. This is where we take this type of a device and we now spread it along the length of an optical fiber. This is actually work by Kevin Chen's group, and I've had a chance to collaborate with him on this over the years. This is where you actually can inscribe the equivalent of a Fabry-Perot interferometer in the core of the fiber, and then you can space those along the length of the fiber. By varying the length or the distance between those features, you can vary the corresponding overall frequency spectrum associated with their signal, and then you can separate that out in order to be able to measure things like temperature for each of those individual sensors and to identify the location of that sensor as well. The other thing that you can do, again work by Kevin Chen's group, is you can look at things like quasi-distributed measurements of acoustics, and then also look at taking the large amounts of data. So with acoustics, you don't just get a point measurement, you get a frequency spectrum. So it's a tremendous amount of data, because for every point, you may have thousands of data points associated with the frequency spectrum. So you end up with very large data sets. One of the approaches to manage this is to then take artificial intelligence or neural network-based approaches to take all of that information and then correlate between patterns of the data and events or features that we want to measure. This has a lot of applications in things like measuring infrastructure security, local corrosion, and other things that Kevin's group has been looking at over the years here. So we can also apply sensing layers to fibers, just like we did with the surface acoustic wave, and we can actually apply very similar sensing layers. So this is an example where we're applying a metal organic framework, again for CO2 and methane sensing, but we're applying it as the coating on the core of an optical fiber. We again get to take advantage of the rapid reversible response of the metal organic framework and the selectivity to CO2. The unique aspect about integrating sensing layers on a fiber is, though, so notice that on this slide I don't say whether it's point or whether it's distributed. The reason for that is that in the case of optical fibers, in principle, a sensing layer could be either a point measurement, or you could expand it to a distributed measurement by combining that with distributed interrogation methods. So you have the ability to choose whether you just measure at one point or whether you measure all along the length of a pipeline, for example. We've also looked at doing things like incorporating plasmonic materials for temperature and gas sensing. In this case, what you're doing is you're embedding a nanoparticle in a matrix. This nanoparticle has a characteristic optical feature associated with it called a localized surface plasmon resonance. That feature depends on temperature. It also depends on the carrier concentration of the electrons in the particle, and that is related to gas phase chemistry. So by using a relatively simple type of a material, we can interrogate different wavelengths because of the difference in the gas phase and the temperature response. And by interrogating different wavelengths, again, we have something that starts to look like the analog of an optical version of the electronic nose. So we talked about the wireless version of the electronic nose, which was multiple arrays on a SAW device. Now we're talking about an optical version, which may be just one material, it may be multiple materials, but the array corresponds to how many wavelengths we do our measurements at. And so this is a kind of a new emerging area within this field where we can get a large amount of information from a very simple, very low cost single sensor element by using this type of a multi-wavelength approach. We can also replace plasmonic nanoparticles with things like palladium. So palladium has a very selective response to hydrogen. When it interacts with hydrogen, this allows for a change in the characteristic optical constant. And this allows for a very selective response that we can incorporate into an optical sensing platform. A key application for this in the energy infrastructure monitoring space is in transformer monitoring, for example. So as it turns out, in large transformers, one of the key ways that you measure the state of health of the transformer is based on its insulation oil. So you measure the local temperature, you also measure the chemistry. And so if you start to see hydrogen or you start to see hydrocarbons, that's a signature that the insulation oil is degrading. And so for large transformers, companies will pay upwards of tens of thousands of dollars to monitor that in real time. But if you look at the transformers that are out on the pole tops as you drive down the highway, those have virtually no sensing instrumentation associated with them. The reason for this is that you have to have a very low-cost solution for this type of a sensor, or for this type of a transformer. So if you take an optical fiber sensor, you integrate on gold nanoparticles in a matrix, you integrate palladium nanoparticles on a matrix, we can take advantage of both of the two types of sensors that we just talked about. We can use extremely low-cost photonic-based measurement systems, a low-cost LED, a low-cost photodetector. This can be integrated onto a fabricated device, integrated device in the future. And this allows us to measure signatures of hydrogen as well as temperature at a cost which starts to be compatible with the deployment in actual distribution transformers as well. So this can start to give some visibility into assets which were previously not possible. Okay, the final area in optical fiber-based sensing is the area of distributed sensing. And so in this case, what we're basically doing is we are measuring the scattering as a result of a pulse of laser, a laser pulse which is sent down the fiber. There's a ton of different techniques that are all different ways that use different types of scattering, whether it's Rouen, Raman, or Rayleigh, and then different ways of doing the interferometry on the back end, whether it's time domain or frequency domain or low coherence based. All of these have different characteristics in terms of the ability to get range that's long or short, resolutions, and so this is a whole field in and of itself. The review article that I mentioned does a reasonably good job of really going through some of the trade-offs and also mapping some of these different approaches to different types of energy infrastructure that you might monitor, whether it's the subsurface or whether it's pipelines. So one of the things that has been done in recent past, again in collaboration with Kevin's group, is the idea of actually controlling the amount of backscatter so that you can control the signal-to-noise ratio. And in addition to controlling the signal-to-noise ratio, you can also enhance the temperature stability. This is a very nice tool, and this allows for, in addition to optimizing your interrogation method, it now allows you to optimize the overall signal-to-noise ratio of your sensor as well. So whether you want to measure a meter or 10 meters or you want to measure a kilometer, you have the ability to tune that. Okay. This is one example of a custom interrogation system which is being currently built and constructed by a colleague at NETL. His name's Ping Liu. This is a Rouen-based scattering system. One of the unique features of this is that he's looking very carefully at optimizing this overall system so that he can get the best possible performance metrics out of it. And this is intended for the applications of natural gas pipelines, but it's also relevant for the application of electrical transmission lines as well. So some of the ways that you can do this, you can look at, in addition to your standard interrogation, you could look at amplification methods by using an additional pulse, which causes some additional scattering. You can look at optimizing your fibers. So your fibers, depending on their characteristics, again, enhance backscattering, enhance response. allow you to optimize the Brouillon scattering and the Brouillon resolution. The other thing that can be done is starting to analyze the data that comes out of the measurement using techniques such as machine learning or artificial neural networks. So this allows you to take this huge amount of information over 150 kilometers of fiber where you've measured a data point at 1 meter, and that can then be very rapidly analyzed, and it can also be analyzed with higher accuracy than using traditional methods, which would be a post-processing scheme. So these are all examples of ways that you can kind of push the envelope in terms of distributed interrogation. Okay, with all of that, what I'd like to do now is just to mention an example of a review article that is under review right now. The colleagues I showed on the first slide, as well as a few colleagues who are on the phone right now, all contributed to this, and I had the privilege of contributing as well. This was really a critical look at the area of quantum information science. I thought this would be a good topic for this crowd. In particular, there's a section that overviews quantum sensing, but it takes a little bit of a different view on quantum sensing, and my comments here are going to kind of reflect that view, which is it looks at what are some potential practical ways that new ideas that are up and coming in quantum sensing might be integrated with some of the types of sensing platforms that I just discussed. So to do that, we'll first talk about what a quantum sensor is. I think many here on the phone will be familiar with that, but for those who aren't, it basically requires a discrete multi-level system. This could be electron spins, for example. It requires the ability to both initialize the state and then read out a well-defined state. It requires the ability to coherently manipulate the system. And ideally, if it's being used for a sensing application, particularly if we're using it for a practical application like monitoring energy infrastructure, we would want that system to be interacting selectively with the variables that we care about most, whether that's temperature or that's magnetic field, pH, whatever parameter that we're interested in. So there are multiple types of quantum sensors. Examples of non-photonic-based quantum sensors would be qubit-based. Many that you see out in the literature are spin qubit-based. These typically have 2 levels, and examples and the energy gap between those levels responds to the environment. And the examples of that would include vacancy centers in silicon carbide, rare earth doped solids, nitrogen vacancies in diamond, and others. There's also photonic-based approaches where we start to look at squeezing photons so that we squeeze their noise in either phase or amplitude at the expense of the other corresponding parameter, as well as entanglement of photons as well. So there's a number of different types. The ones that are most relevant to the types of sensing platforms that I just overviewed here would be the non-photonic type, where we might be integrating some type of sensing material onto either a surface acoustic wave device or an optical fiber sensor. And then quantum interferometry, remote target detection, and spectroscopy, which would be related to the optical fiber-based. So in terms of practical aspects, in putting together the review article in question, one of the things that was a primary focus was how do we what are the materials that really seem, so if we start to look at it from a materials perspective, what are the materials that seem most relevant for practical deployment in energy-related applications? And the ones that really stick out are some of the most well-studied. So diamond, nanodiamonds, nitrogen vacancies in diamonds, as well as various types of characteristic defects within silicon carbide as well. So those are 2 very promising directions to look moving into the future. There's also some examples of other emerging materials. These include rare earth doped solids, metal organic frameworks, defects in silicon, boron nitride. Based on these different materials, you can measure magnetic fields, electric fields, temperature, strain, pH, pressure. If you review the literature, what you do get a little bit concerned with is there does seem to be some pretty substantial cross-sensitivity to multiple variables in quantum-based qubit sensing modalities. And so moving forward, if we're really interested in finding ways to leverage the advantages of these materials in practical device platforms, we really need to think carefully about either eliminating cross-sensitivities or finding ways to interrogate these materials so that we can separate out those cross-sensitivities. So in the case of vacancy centers in diamonds and nanodiamonds, there's a number of different techniques which are used to get information about the spin states within these materials. One of the most common is the optically derived or optically detected magnetic resonance-based techniques. These are very well known for measurements of magnetic fields. This is because of the splitting of the spin states associated with the application of a magnetic field due to Zeeman splitting. And this shows, for example, how we can measure fluorescence. And while we're measuring fluorescence, we can also apply a microwave of characteristic frequency. And as we sweep the microwave, you see that we get characteristic resonance peaks in the fluorescence, which are related to the splitting due to the application of an applied magnetic field. And so this can be very effective at sensing very low-level magnetic fields. There's also other ways to interrogate these types of materials as well. One of the other practical ways is just through zero phonon line emission-based methods as well. One of the advantages of this type of a platform is that it is relevant for room temperature operation. Anything that requires active cooling, cryogenic temperatures, is going to be very, very challenging to deploy in some of the applications that I just talked about, particularly because of the fact that many of them actually are extremely high temperatures or harsh environment conditions. Another example of a material system that looks promising is silicon carbide. So these have a number of different types of defects which can form in color centers, which can create possible opportunities for qubits with different characteristics. The most commonly explored so far are silicon vacancies and die vacancies. One of the advantages in this case that we've seen in looking through the literature is there do appear to be certain types of color centers where you have less cross-sensitivity to certain variables. So you may see sensitivity to magnetic field, but not as much sensitivity to some of the other variables. So because of the large number of polytypes of these materials available, as well as the fact that there does seem to be some degree of selectivity, these are materials that are of interest moving into the future. And then for materials that are a little bit further out on the horizon but very interesting, these would include rare earth doped solids, where you can use characteristic energy states of the F and the D electrons to be used in things like optically derived magnetic resonance, and some of that's been demonstrated for materials such as cerium in YAG-based crystals. Metal organic frameworks are a very interesting class of materials. One of the reasons is that there's so much flexibility and control over how we place various atoms and various ions within a metal organic framework because of the fact that it's this hybrid organic and organic structure. In addition to introducing controlled qubits, we also could have the potential for introducing controlled spacing between qubits and understanding interactions between qubits. So we are using metal organic framework materials currently with some of these sensing platforms, and moving forward, this may be an interesting direction to go as well. So this is just kind of a table to have listed. It's in the review article, so once that gets formally published, it'll be publicly available. Just as a quick snapshot, you see different types of interrogation methods of quantum sensing materials, whether it's zero phonon line emission, optically derived magnetic resonance, spin relaxometry. Depending on the type of interrogation, the type of material, we've seen responses to temperature, electric field, chemistry, for example, pH, which would be very relevant. And these are some of the example applications, which could include pipelines, transformers, and others. One big challenge, though, is if we take some of these new and emerging quantum sensing materials and we try and integrate them with practical device platforms, that integration is not trivial. And so this is an example reference, and this is really good work. I like this reference, but it's very difficult to envision this type of a scheme in some type of distributed sensing modality, for example. So here's an optical fiber. It's a telluride glass fiber. It's been doped with nanodiamonds, which have nitrogen vacancies, which can be used as qubits. It's being illuminated with a laser exterior to the fiber, as you see. And then it has local introduction of microwave energy by an antenna, which is placed in proximity. So based on this, they can measure the characteristic emission by the guided modes within the fiber, and then they can map that out with a CCD. So this is a really interesting piece of work. They can use it to measure local magnetic fields. But in terms of being able to do something like this all along the length of kilometers of fiber becomes a major challenge. So one of the key challenges moving forward is how do we rethink the way that we integrate sensing layers with these types of device platforms which are so practical for energy applications? And conversely, can we focus more on some of the interrogation methods that actually would be most easy to be integrated with these types of sensing platforms? The area of distributed fiber sensing, as I mentioned, there's a ton of optimization to be done there. That's an entire field in and of itself, even without going to the classical limits. However, if we can achieve the optimal limits of the performance of current distributed fiber sensing, it is at least possible that we can pursue advances on that limits beyond what's possible with traditional classical limits. This is a conceptual version of a quantum distributed acoustics system. This was put together again by Ping Lu at the National Energy Technology Lab. I'm not going to go through this in detail. All I'm going to basically say is that this is an example of a practical system which is operating at telecommunication wavelengths, which again is the primary wavelength for long-distance telecommunication fibers. And the goal here would be to really allow for measurements of phase shifts at the lowest possible signal level, which in the case of distributed acoustic sensing would mean that we would be able to measure very, very small level vibrations or acoustic signatures, which may be otherwise inaccessible. Similarly, a lot of the types of sensing devices on the fiber platform that I talked about, so whether it's surface plasmon resonance based, whether it's fiber Bragg grating based, whether it's Fabry-Perot based, the mechanism of sensing is really related to measuring phase differences, which result as a result of temperature changes, as a result of acoustic changes, strain changes. So we can certainly envision that, at least in principle, using phase squeezed photons, for example, could allow us to improve the performance limits by sharpening up the uncertainty in the phase and allowing us to measure signatures that we wouldn't otherwise be able to. Again, this is kind of a schematic distributed guided optical wave setup, which would allow for the generation of squeezed photons and also the detection of squeezed photons with phase-based discrete devices integrated on in an overall guided wave system. And so this is one example of a practical implementation. Okay. With that, I'm going to basically conclude. So just the high-level points here. Energy infrastructure sensing is an important area. We can think about, those of us who are in the field, we think about sensors based on their attributes. These attributes are different depending on which applications we might apply them to. As it turns out, passive wireless and fiber optic are really advantageous for a number of applications in this space, which is why there's been a lot of work done in the past. We can use sensing materials to really make them most perform and have the most functionality, but we also have to optimize the interrogation and the telemetry as well. Moving forward, in terms of thinking more quantum about these platforms, we would think about nanodiamonds and silicon carbide, which are sort of established quantum sensing materials that may be practical and relevant. Some of these emerging materials, like quantum metal organic frameworks. The ability to operate at least at room temperature, preferentially higher, is something that we would really need to think about carefully. And also the area of fiber optic sensor device and interrogation and integration. You know, whenever possible, if we can do all optical interrogation methods, it's a lot easier for the fiber platform. If we can do it at 1550 nanometers or nearby, it's desired. There is the potential for improving sensitivities, at least in principle, both from the perspective of distributed fiber optic sensing as well as discrete devices which are based on phase shifts. So with that, I'm going to conclude, and thank you very much for your time.
Thank you.
Sure.
I'm sure everyone's clapping along with something.
Remote
that's
clapping.
great. So, yeah, Paul, although I work with you a lot, I still learn quite a bit from that part of work I don't know. So, so let me just open the floor for any potential question.
Shane, I saw that you had a question during the talk.
Jeremy, do you have any question?
Yeah, so, yeah, I'm really, amazed at the breadth of the research that you're doing. And I'm really excited to see, actually, I'd be really interested in getting a copy, advanced copy of this review article on quantum sensing.
Yeah, we'll talk to the folks over at EDTL and see if it's okay.
Yeah, so I think I see Bob Devity on the line here. You know, there's decades of experience in silicon carbide and especially examining defects. And I don't know if this is something that that you'd be interested in pursuing experimentally, or if this is really more just a survey to see whether what are all the possible things that could be done. I mean, I understand that the need to have something that works practically, and a lot of the work that has been done so far have been under controlled environments, and
So yeah, I mean, I think in short, I think there would be interest moving forward in talking about, possible collaborations in this space. I also have, and Kevin and I have talked about some ideas actually for creative ways of doing this in a way that's more practical than what's been done in this reference. So both from the perspective of how can you take some of these ideas and put them on the fiber platform, and then also, looking at, is it really feasible to get some of these advanced quantum sensing materials onto either a point-based fiber sensor or a distributed fiber sensor, and really understand what the potential are. I think that would be of interest moving forward. Kevin, do you have any thoughts on that?
Yeah, so the one of the key question that we would be bothered by is that the entangled photon you're launching to a fiber. For example, we launched the entangled photon in the coupled two-core fiber. So I think they tend to lose entanglement after tens of meters, although people say that you can maintain entanglement for a few hundred meters. So we now will be able to reach that. We'll only be able to reach like a few meters, then we won't be able to actually confirm they're entangled. So that's like Jeremy mentioned, that's an issue that we don't know. We still have to.
Yeah, and that's one I didn't actually mention. I mean, that's an area where you might even be looking at alternative fibers that try and minimize and maximize the length over which you can maintain coherence, right? Because a lot of that is related to losses and scattering, and so that's another area where you'd really have to kind of rethink the way that we're thinking about distributed fiber optics currently.
Okay, so we still have quite a few audience here in the room. Does anybody has other question?
I was curious, for those MOFs, would it be like a single atom dopant in an entire MOF lattice, or what would it be like?
So that could be an example. Is Scott on the line? Scott, do you want to speak to that? I think you were the one who was really interested in this area.
Yeah, so Dana Friedman and another group at Japan have both been working on this, and I believe what they're doing is you actually have things like copper porphyrin, like metal complexes, and they can either be the actual metal centers, or you can have a regular set of metal centers and linkers, and then periodically spaced within the MOF, you'll have these metal complexes. So that's the typical approach. I think there've been maybe 3 or 4 publications so far on this, so it's definitely a fairly new field. But yeah, it's usually copper porphyrin. I think there's a cobalt complex they use, so you just have these metal spin qubit complexes as part of the actual MOF structure.
Yeah. Okay. Yeah, I'll have to look in the Dana's work. I feel like so many people at Pitt do MOFs. I wasn't sure if anyone had worked on that here.
Yeah, I'll send you. I should have the articles with me, so I can definitely send those to you.
Yeah, thanks, Scott. So okay, yeah, this is very interesting. Does any other people has question in the room? Okay, Jenny, Jeremy. Oh, go ahead.
Professor Chen is so what do you think approaching from a research standpoint, what do you think the next steps are? Do you think it's more on the material science side of things and still just trying to develop better and more practical quantum materials? Or do you think it's taking existing quantum materials and just finding new techniques to isolate the sensing from, unwanted variables that only responds to variables of interest? What are the next research steps that make the most sense to pursue in the short term?
I think Jeremy will be the best person to answer this question, just from perspective, because I work in the room temperature. So I try to extend this kind of experiment in a fiber base. So we want to actually try to maintain the entanglement of long propagation distance, and we encounter many challenges here. So that's something that the bothers me a lot for this type of technology. But I think Jeremy has many years experience, and you are really the leader here. So maybe you can shine the light. I think this is a very important question because NETL network is very interested in this technology, and they could put money invest in this field. So I think we should probably think this through.
Yeah, I mean, I think that, you know, the science and engineering aspects of this, these are things where both sides have to move together, right? I mean, but at the same time, if you're doing the science, you can afford not to necessarily have to worry about the practical applications. But if you want to have an impact in some type of application, then at some point you have to narrow down and say, okay, I'm now going to constrain myself to working with materials that have these properties or work under these conditions, and then ask yourself, well, under those boundary conditions, what can you do? But I think also from the other side, being able to think about other possible systems that may not initially meet the criterion, like what you're saying, Kevin, about you know, if you have something that, you know, can go a kilometer, 100 meters, let's say 10 meters, and you need 100, well, there's still some benefit to, you know, to doing research on something that doesn't quite meet the specs, but in anticipation that there may be developments that are outside of the domain that you immediately have access to. And I think that that's really where having this awareness, this cross awareness of what people are doing in material science, engineering, and the basic sciences, I think that that's where it's really important to be aware of that, so that you can project forward and not just be limited by what you can do today, but be thinking about how people can team together and to really meet these demands. And as Paul pointed out, the demands of, you know, quantum space are, you know, they can be brutal in some cases, and but on the other side of it is you're getting capabilities that you didn't have before. So it's really yeah, that's I guess the perspective, general perspective.
So I guess the science and engineer has to scientist and engineer has to find a point of merging point so that we can move forward. I think that's very important information we should convey to the NETL when they actually issue FOA or they want to support some research. Just say that you can't be that practical when you issue FOA for the quantum science or technology. That's something that I think you should actually you should convey to them, or we should collectively convey to them. Just let them know that this is a long-term investment, not just a short-term kind of engineering TRO level improvement, that type of thing. So I guess that's all, Jenny, right? So we are 2 minutes over now, past 5. So if there's no,
but you got here 5 minutes late, so.
Oh, sure. I apologize for that.
He had to take the opportunity.
So I guess, Jeremy, once you get a PowerPoint form, Paul, maybe you can share with everybody.
Well, I think they need to decide how they want to distribute, but.
Oh, you can have the slides, no problem. I'll ask
the
about
slides.
The review article.
Yeah, the slides.
Yeah, the slides are no
Absolutely.
problem. And I think the review article is probably fine, but I'll talk, Scott and Hari, we should talk to them and make sure. But I think it's probably, it's going in for review. So as long as somebody's not a reviewer, it shouldn't be an issue.
Yeah. And I can post your slides online with the YouTube video too. So anyone can get to it.
Okay. Let me thank Paul again. So for this.
Sure, thank you.
Yeah, thanks.
Yeah, thank you, Paul. Yeah, really enjoyed this.
So if we do not have any further questions, let's just say have a good evening, everybody. So we will see each other next time.
Thank you.
Thank you.
Thank you so much. Great to see so many familiar faces.